afternoon. Yeah, afternoon. We're finishing off divergence theorem. So here goes. Just going through the last 3 questions. I'll just take it to a point where I think it's easy to leave it. In question 9 then, we're getting this guy called the flux. Here is your vector field, and S is the surface described like this. And this is going to be the hard part. How to get your 3D region out of a surface that's bounded by various surfaces. Now in question 9, they actually give you a picture, but I'm not sure the picture itself is very helpful, but let's show you anyway. And then I'll return back to my working. It's this picture here. So this sloping slice is the x plus z equals 1 guy. And this curved surface going that way is what x equals y squared looks like. And so the region that we're trying to generate is this region here, right? So can you imagine you're trying to describe this 3D, I don't know, we'd call it a wedge in terms of x, y, and z values, okay? So we're going to have to say z goes from here to here, x goes from here to here, y goes from here to here, right? That's triple integral, right? You need an x, a y, and a z limits. And that's where the fun will start. Because once we figure out what that is, it's really plug and chug. But before we work on that surface, let's just get the divergence fella out the road so we don't need to worry about that. There's our P, there's our Q, there's our R. And the divergence is, oops, P, it's a P, with X, Q, with Y, R, Z. If you differentiate this guy here with respect to X, you get 7Y. If you differentiate this guy with respect to Y, you get nothing. And if you differentiate this guy with respect to Z, you get 2Z. So let me check it. X is the only guy, 7Y. There aren't any Y, so you get nothing. And that doesn't matter, you get 2Z. Okay, so there is our divergence. That typically is not difficult. Would you agree the divergence is not where the problem ends up being? It ends up being in getting this region R. Now, I'm not going to go back and forward to that picture. There's just too much going on in that picture, but it roughly looks like this. Right. Now, I've got this guy equal to 1, and I've got this guy equal to 0. So I'm going to use that to get my limits for Z. And if you rearrange this, you get Z is 1 minus X to Z equals 0. That would essentially be on the surface down to the floor. The floor would be Z equals 0, and this is this surface here. And that's the guy they called X plus Z equals 1. Are you comfortable about the Z range thing? Basically the vertical distance. Now, if you then take that wedge and you only focus now on what's happening in the X and Y world, you had an equation called X, what was it? Here we go, X equals Y squared, which basically is that guy, okay? And I'm going to use that one to generate the X's. Are we comfortable with that? Any issues with that? Okay. And that means I only have one last guy to worry about. And I guess that's going to be my Y value. And I need my Y value to, I'm trying to find that picture again, because I'm sure there's something in that picture that's going to give me the Y. And Where are you, picture? There's an axis going this way and there's an axis going that way. And this is the X, this is the Y. And I need to find here. And, you know, there's a thing going this way I need to find here. And so I'm trying to figure out what I've got. Oh, if Z equals 0 makes a floor, then X plus 0 gets me 1, which means X equals 1. And if you do X equals Y squared and you make this 1, that tells me who Y is. Okay, I got the -1 and 1. So imagine this curve coming down and hitting the ground, and we're looking at the edges here, here and here. And those edges happened at an X value of 1. And an X value of 1 gives you a Y of -1 and a +1. Does that make sense where I got that from? Okay, we are good to go. So to find this surface integral called the flux, we will go and do a triple integral of the divergence, dv. And this is going to have a Y value from -1 to +1. Check. Now, who do I do in the middle and who do I do at the end? Because there's a right order and there's a wrong order.
I think in the middle, it should be the Y squared and the 0.
And then okay, it's correct order. What made you go that way?
Because it has to the Z has to transform into the X before you mess with things.
Yes, that'll do. So since I crushed all these together, let me rewrite it again. You're going to have this guy. You're going to have this guy. You're going to have this guy. The divergence is nothing interesting. We're going to do a Z first, an X second, and a Y third. And I'm going to dot that. Would you agree that is just one ugly triple integral? I mean, there's nothing horrible to integrate. It's just going to be polynomials of various kinds. I think that's done. So let's move on to question 10. And this one has a little difference in it. Going to get the flux. The vector function, vector field, is described as the magnitude of a vector R, where R is this guy. And S is all this stuff. But well, let's figure out this guy first and then we'll focus on that. Since R is described as that, which is essentially the position vector, the magnitude of R is X squared plus Y squared plus Z squared. So when you put those two together, what you're going to get is this guy times him, this guy times him, and Z don't have enough room, this guy times him. There is a F. So I guess I should move on. That's for later. With the divergence. So we're going to differentiate with X, Y, and Z. And this guy is P, this guy is Q, and this guy is R. Would you agree that there's a kind of pseudo symmetry here? And by that, I mean that if I get this answer, shouldn't I be able to make a reasonable prediction on the other two? So let's put a little boundary line here. Let's differentiate this guy, and let's differentiate him with respect to X. So it's definitely a product draw because there are X's in both pieces. So it's going to be F dash J plus F of J dashed. You differentiate this guy, you get 1. You leave this guy alone. Plus you leave this guy alone and you differentiate that guy, which is 1/2 x squared plus y squared plus z squared to the negative 1/2. And it's a chain rule times 2x. So you end up with x squared plus y squared plus z squared to the 1/2. 2 and that cancel, x and x gets you an x squared with a x squared plus y squared plus z squared to the negative 1/2. Ooh, yikes. I do not like this one, but I'm still going to have to do it. Okay, I need style points. I need to try and make this thing as pretty as I can. Well, the only thing I can see that's usable is the fact that there is a common factor. It's just a weird one. And when you have a choice between a common factor to 1/2 and another one to negative 1/2, you always take the smaller of the two. So this guy's used up, so you're going to have plus x squared. And this is the weird one, but I've done this in my Calc 1 class, so I know you've seen it maybe 6 months ago. You take 1/2 and you subtract negative 1/2 from it. That's how you pull out a common factor. You take the half power you've got and you subtract a negative 1/2 from it, which essentially means you add 1. So you end up with x squared plus y squared plus z squared to the power of 1. This guy is now going to go on the bottom. And these are going to get added, and you're going to get 2x squared plus a y squared plus a z squared equal to that. And after all that hard work, we have 2x squared plus y squared plus z squared all over the square root of x squared plus y squared plus z squared. And that was only to find that guy. I do not want to do that again. I need to find what that guy is equal to. I already know what this one is equal to. I want to find this guy. Make an intelligent prediction on what you think the second derivative would be based on a kind of pseudo symmetry that's going on here.
Squared plus 2y squared plus z squared over the same square root.
I'll just call it dotted square root. Correct. And x squared plus y squared plus 2z squared over the same ugly square root. Does that seem reasonable based on the first one? That there is a kind of pattern and you just follow it. Now, we know what the div is. The divergence is what you get when you add these three together. If you add this one, and this one together, they all share the ugly square root on the bottom. Right, that's a common denominator. This one plus this one plus this one will get you 4x squareds. This one plus this one plus this one will get me 4y squared. And this one plus this one plus this one will get me 4z squared. So you're comfortable about the divergence? This guy plus this guy plus this guy combine to give you that. Again, we're still working on making things pretty. Can anybody see anything that you could do to simplify this in some way?
Pull out a 4.
Yeah, why don't we start with that? Have you noticed that the top and bottom both have x squared plus y squares of some type? Because I'm going to use that on the next line. That's like a, and that's like the square root of a. Don't they interact? Can't you cancel them in some way? If you have a full 1 on the top and a half power on the bottom, can't you cancel them? What would they cancel down to?
Wouldn't it be the square root, but in the top?
Yep. Okay, are we comfortable that that was a bit of work, but we have now got a reasonably nice looking divergence? Now, although we haven't come to the next bit, when you see x squared plus y squared plus z squared going on, and you know it's a treble integral, where do you think the coordinate scheme might lead to next?
Spherical.
Yeah, and that's where it's going to be. Even although we haven't figured out R, that's actually what's going to happen. So since I've told you it's going to be R, can we just call that guy 4 rho right now? Because that's what the square root of x squared plus y squared plus z squared gets you, right? Even although we haven't got R, it's going to become 4 rho, right? So let's look at that region R now and sort it out. Better put a bubble around that because I know I'll forget it when I need to see it. And somewhere in this question, here we go. It's a hemisphere. Okay, if you rearrange this information, it's the same thing as x squared plus y squared plus z squared equals 49. Will you trust me on that? That's what it eventually becomes. And it's a hemisphere and it's the xy plane. So it's the hemisphere, there's the xy plane. The floor is xy and it's the top half, right? Why is it the top half? Because it says plus, right? That's good. Now, what else do we have? Well, we have a disk, x squared plus y squared less than or equal to 49. And we have the xy plane. Pretty much that is contained inside that. Because the minute I make that 0, don't you get x squared plus y squared is 49? And it's the guy inside it. So that hemisphere was really all I needed. That there was probably incidental information. So for a half a sphere, rho goes from 0 to 7. Theta goes from 0 to somebody, and phi goes from 0 to somebody. So all I need to do is figure out what goes here and what goes here, and we're good. Now, if I put in my very bad x and y axes, can you see the circle they're talking about? Now, because it's a circle, are you happy with the 2 pi? You rotate the whole angle's worth, right, on the xy plane. The rho is not 0 to pi. Rho starts on the y-axis and then you rotate this way. And if you want to get the whole sphere, you rotate all the way to the bottom, right? So that would be 0 to pi upon 2. You comfortable with that? Same as hemisphere. phi is 0, the vertical, and then you finish when you get to here, right? That generates the entire sphere. And that guy is pi upon 2. Are we good? Yes, no, maybe? Any questions? Okay. I'll put the package together then. That's the next question. Where did, oh, here we go. That's not the one. There we go. That's the divergence. Let's put all the pieces together. So the surface integral, called the flux, is going to be in polar, the divergence, which is 4 rho. We are going to do rho equals 0 to 7, check. Theta equals 0 to 2 pi, check. Phi equals 0 to pi upon 2, check. Times, and our dV gets replaced by the rho squared sine of phi d rho d theta d phi. And those two bits are like the r dr d theta thing, right? That's the two terms that you get when you do spherical. So if I put this package together, that gets me, well, let's do it in the order you've got. I've got a sine of phi, and that's going to go from 0 to pi upon 2. And then I'm going to have a theta going from 0 to 2 pi. Aren't any thetas mentioned, so I'll just use one. Then I'm going to do a rho equals 0 to a rho equals 7 of 4 rho cubed d rho. Are we good with that? Variable separable. Right. If you do this guy, you get a negative cosine evaluated from 0 to pi upon 2. If you do this one, you just get 2 pi. If you do this one, you get rho to the 4 evaluated at 0, evaluated at 7. Plug in that guy, you get negative the cosine of pi upon 2, which is nothing. Take away negative 1 is plus 1, so you get 1 out of that. That guy's still 2 pi, and this guy gets you 7 to the power of 4. I have no idea what 7 to the power of 4 is. 2,401 times 2 then. So I have 4,802 pi. Are we good? Christian. God, yeah. That better be your wife.
Maybe. I don't know.
Just some random stranger. Okay. So, moving on then to our last question. Is this? I think that's not our last question. That's the one we just did. Our last question was this one. Yeah. And we get to that part I always feel kind of sad about. Our last question, the last thing we're ever going to do in Calc 4. And no fireworks ever, no marching bands, no nothing. It's just, here's a question and we do it. But let's do it anyway. We're being asked to get another flux. Nothing too special here, it's just long and big. And this is our vector field. And S is basically this guy, and it's in the first octant. So actually, it's an easy question. So I'll call this P, call this Q, I'll call this R, and we'll do the divergence first. I think I may have to go over here to get everything in. Right, if you differentiate this guy with respect to X, you'll get a cosine of X and a cosine squared of Y. If you do this guy here with respect to Y, you're going to get 3 sine squared Y times the derivative of sine Y, which is cosine Y, followed by that guy. And if you do this one, yikes, you get 5 sine to the 4z times the derivative of sine, which is cosine, with a cosine 6x. That's ugly. Is there anything I can do to make this pretty? I could pull out a cosine. Nah. Could I pull out a sine? Nah. I can't see anything to make that even vaguely pretty. Oh, God in Himmel. Okay. What about the region R? Well, since it's in the first octant and these are the guys you're going to deal with, we really don't have anything to think about. It's going to be 0 for the Y's and the X's and the Z's. And so this guy is going to be the integral from 0 to pi upon 2, 0 pi upon 2, 0 pi upon 2. This ugly expression, cosine X, cosine sine Y, plus that fella. Don't even know enough room to put them in. Plus this guy. And who cares what order, because it won't make any darn difference. I think X, Y, Z is as good as an order as any. And we are looking at one horrible, horrible answer. So I'm just going to tell you what they give me for mine, because that's all they tell me. Evidently, it's negative 1964 pi squares. Oh, and the good news is that everybody's answer is going to be 1964 pi squared, because that question doesn't have any red numbers in it. So everybody's getting the same numbers. Now, all I need to do is make sure that I've written it down correctly for you then. That's a sine and a cos squared, check. That's a sine cubed and a cos 4z, check. That is a sine 5z and a cos 6x, check. So that's going to be your answer. Have fun trying to prove it. But we are finished. That's it. There's nothing left to do. Come on, there should be some disappointment here. No, it's woohoo, we're finished. Okay. Well, why don't I give you a little break then? Put your last name down and bye-bye, and I'll hang out for any questions. Starting tomorrow, you are going to have some really good questions for me concerning the final, right? Because we're basically revising now until the end for that. And I think that's everything.